Makaku once remarked that we will need to rewrite our textbooks on the beginning of the universe. Everyone has been eagerly awaiting a particular image, which has now been made public. This image from the James Webb Telescope reveals unusual processes in the cosmos that challenge our scientific understanding. Since the launch of the telescope, not only have our theories on the universe's origins been tested, but even exoplanets have begun to defy our understanding of physics completely, turning our ideas upside down. What new situations and answers can scientists discover in response to these provocations? We are currently witnessing a complete upheaval of the old rules in science. The James Webb Telescope is revolutionizing our perception of the universe, and each new image from this marvel of space exploration is groundbreaking. James Webb, the telescope's namesake, would have been proud. Webb was not a scientist but came from a business background. He understood the significance of space exploration for humanity. As head of NASA in the 1960s, Webb advanced space travel significantly, launching the Apollo program and advocating for space probes. Today, scientists are astonished by the capabilities of the telescope named after this pioneer. The images are so clear and sharp that they take our breath away. For the first time, we have complete analyses of exoplanets, some thousands of light-years away. The telescope is revealing to our scientific community that they have been relying on outdated findings and ideas for too long. Initially, many scientists are experiencing uncertainty and discomfort, as everything they believed in may now be proven wrong. Michio Kaku, a popular astrophysicist from the USA, is one researcher who is optimistic about these new developments. Kaku has long argued that our previous theories were incomplete. The inability to unite the world of subatomic particles with the world of formed matter alone indicates that we have not fully understood fundamental processes in the universe. Now, exoplanets are also breaking the laws of physics. It's astonishing. Initially, only ancient galaxies didn't fit into our cosmological models. Then came black holes and gigantic structures over 13 billion years old when the universe was supposedly in its infancy. Now, even planets defy our previous understanding. The latest images from the James Webb Telescope show exoplanets that challenge our previous ideas about planetary formation. The telescope re-examined some of the strangest known exoplanets with its keen eye and unique array of spectrometers. The instruments can break down even the faintest light signals into their individual parts, analyzing traces of elements, gases, evidence of water, and parameters that reveal the size and orbits of distant planets. In the process, Webb finds more anomalies, extremes, and the craziest planets. One remarkable example of these impossible worlds that defy the rules of physics is K2-9b, an ultra-hot Neptune orbiting so close to its star that its surface temperatures are high enough to split water molecules into atomic hydrogen. The extreme proximity to its star leads to a phenomenon scientists call atmospheric blow-off, where the planet's atmosphere is literally blown away from the star. This discovery is unique among all known planetary atmospheres and presents a significant challenge. Webb finds so many exceptions and extremes that it's statistically impossible. K2-9b is so strange that it's almost impossible to classify and represents a blatant exception to all the rules we've established. Let's consider another world that terrifies scientists, WASP-76b, a giant exoplanet with iron raining from the sky on its night side. The planet orbits its star in a tidally locked orbit, resulting in extremely hot and cold sides. Metals melted and vaporized on the hot day side solidify into iron on the far side, then fall to the ground like rain. Once again, scientists are dealing with extreme conditions that impressively demonstrate the physical processes on exoplanets and raise more questions than answers. Particularly fascinating and puzzling is the discovery of planets orbiting their stars in the opposite direction to other planets in the same system. Such discoveries force astronomers to rethink theories about the dynamics of planetary systems and the forces that determine their orbits. WASP-17b is an example of such a world. This exoplanet, found as part of the wide angle.
This material forms molecules and dust, partially obstructing our view of the star and causing it to appear dimmer. In the case of Betelgeuse, the SME resulted in the ejection of a mass 400 billion times greater than what is typically observed during similar events on other stars or CMEs. This amounted to multiple times the mass of the Moon, propelled at astonishing speeds. researchers noted that such an enormous mass ejection from a star's surface had never been witnessed before. The event allowed for the direct observation and examination of surface details using the Hubble telescope, offering a real-time glimpse into the aging and evolution of a dying star. The SME had a profound impact on Betelgeuse, causing it to lose a significant amount of mass in a single event. This occurrence demonstrated that a dying star can experience substantial mass loss beyond its regular annual decrease due to stellar wind. In a way, it was as if Betelgeuse had forcefully expelled its upper layers and was presently in the process of slowly recovering from the aftermath of this injury. However, following this dimming event, the star's behavior has undergone a change. Previously, it would pulsate or alter its brightness every 400 days, but now it is pulsating every 200 days. Betelgeuse is classified as a semi-regular variable star, meaning it experiences multiple cycles of fluctuating brightness due to variations in its size and temperature. This red supergiant is known to exhibit two main periods of light pulsation. The first period lasts 400 days and is believed to be caused by pulsations in the fundamental mode. The second period is a longer cycle of approximately 5.6 years, and its origin remains unknown. In their research paper, scientists utilized computer simulations to gain a deeper understanding of the events that transpired. They proposed that an unusually hot gas current, resembling a large and intense bubble, emerged from within the star. These occurrences of hot gas bubbles occasionally arise due to the star's turbulent and convective envelope, which can be likened to a pot of boiling soup where the material is constantly in motion and mixing. As this hot bubble ascended and broke through the star's surface, it triggered the ejection of stellar material. Interestingly, it also disrupted the star's regular pulsation pattern. The star's surface continued to expand, while its deeper regions contracted, causing the star to transition from its customary 400-day pulsation to a new 200-day pulsation. Astronomers anticipate that the star's regular motions will gradually stabilize the unusual pulsation over the next 5 to 10 years, ultimately restoring Betelgeuse to its normal 400-day pulsation. Regarding the possibility of a Betelgeuse supernova, astronomers speculate that it could occur at any time within the next 10,000 to 100,000 years. Based on factors such as the star's color, brightness, size, and estimated age, scientists suggest that Betelgeuse is currently in the early stages of helium-to-carbon fusion. This process must continue through oxygen, silicon, and finally, iron before the star's core collapses under its own gravitational pull, leading to a cataclysmic explosion. Since Betelgeuse is located 650 light-years away, any supernova event happening at present would only become visible to us after 650 years. Due to the limitations imposed by the speed of light. Therefore, it is highly unlikely that we will witness the star's dramatic demise during our lifetime. The unique thing about Betelgeuse is that we can actually see its surface, which isn't the case for most other stars. This gives us an incredible opportunity to learn about how big stars like Betelgeuse behave as they get older, including these kinds of surprising mass ejection events. Recently, astronomers made a bone-chilling discovery. For the first ever, they observed a star eat its own planet 12,000 light-years away in the constellation Aquila. Betelgeuse, with its intriguing name and prominent position in the night sky, has captivated the human imagination for centuries. Its significance extends beyond scientific knowledge, as it has left its mark on pop culture and mythology around the world. Betelgeuse has a rich and diverse origin rooted in the Arabic language. Initially interpreted as the armpit of the giant, some scholars argue that it may represent a hand or shoulder instead.
An impossible findings. Nothing is as they expected. Has science reached an end? The James Webb telescope was created to fill gaps in our knowledge and confirm existing theories. Instead of closing gaps, its findings are tearing new holes in what we consider truths. Some now say that the crisis Webb has triggered marks the end of our old science. As Michio Kaku said, we will need to rewrite our textbooks, but what should we write in them now? No coherent new answers have yet been found, and researchers are desperately seeking new explanations. Unlike its predecessor, the Hubble Space Telescope, which primarily observes in the visible and ultraviolet wavelengths, JWST is optimized for infrared observations. This capability allows it to peer through cosmic dust clouds, study the formation of stars and galaxies, and even characterize the atmospheres of distant exoplanets. One of the primary scientific goals of JWST is to unravel the mystery surrounding the origins of the universe. By studying the light from the most distant galaxies, the telescope can provide insights into the early stages of cosmic evolution shortly after the Big Bang. This includes understanding how the first stars and galaxies formed and how they influenced the development of the universe over billions of years. In addition to studying the distant universe, JWST is poised to revolutionize our understanding of exoplanets, planets orbiting stars beyond our solar system. The telescope-sensitive instruments can analyze the atmospheres of exoplanets in unprecedented detail. By detecting the chemical signatures present in these atmospheres, scientists can infer key properties such as temperature, composition, and even the potential for habitability. The discovery of exoplanets has been one of the most exciting areas of astronomy in recent years, and JWST's capabilities will take this research to the next level. The search for signs of life beyond Earth will benefit from its ability to detect biomarkers, molecules that could indicate the presence of life in the atmospheres of exoplanets. An essential aspect of JWST's mission is to investigate the life cycle of stars, from their birth in stellar nurseries to their eventual death. By observing the processes of star formation, the telescope can shed light on how stars, planetary systems, and potentially life itself come into existence. Additionally, JWST will study dying stars, such as supernovae and planetary nebulae, to understand how they contribute to the enrichment of the cosmos with heavy elements necessary for the formation of planets and life. JWST's observational capabilities are already yielding surprising and sometimes unexpected results, challenging existing theories and expanding our knowledge. This pursuit of new questions, even in the face of uncertainty, is a testament to the ongoing progress of science. JWST marks the dawn of a new era in astronomy, where each discovery leads to new questions and opportunities for exploration. As we continue to push the boundaries of our understanding, the telescope's findings will inspire future generations of scientists and thinkers. The James Webb Space Telescope is not only a symbol of human ingenuity and collaboration, but also a beacon of hope for the future of scientific exploration and discovery.